If you ever want to see exactly how your computer is connecting to the network, opening up the command prompt is usually the first step. In the past, you'd see a tidy 4-block IPv4 address, but today you are confronted with a massive wall of hexadecimal text, your IPv6 configuration. And if you look closely at the end of this long string, you will often spot a strange anomaly, a percentage sign followed by a number or a few letters. Finding a mathematical symbol attached to a hexadecimal address is confusing. It looks like a glitch, a typo, or maybe a piece of URL encoding that accidentally got stuck in the terminal. The symbol appears because of how IPv6 handles modern hardware. Unlike older protocols, IPv6 expects every active network interface on your device, like your Wi-Fi card and your Ethernet port, to maintain its own private local address simultaneously. The percent sign is the physical marker the computer uses to organize those addresses. It identifies which specific piece of hardware an address belongs to, so the system can navigate the overlap. Think about a standard modern laptop. At any given moment, it might be running an active Ethernet connection, broadcasting Wi-Fi waves, and sending Bluetooth pulses simultaneously. This schematic shows those 3 network connections. Under IPv6 rules, each interface automatically generates a link local address, starting with the exact same prefix, FE80::. As this diagram illustrates, these addresses are strictly for local chatter, blocked from ever reaching the public internet. Imagine sending a ping from your laptop to a local wireless printer at address FE80::2. When the computer checks its internal routing table to send that ping, it hits a logical conflict. It sees 3 identical FE80 pathways and has no idea which physical interface connects to the printer. Guessing the Wi-Fi route might get the data to the printer, but guessing the Bluetooth route will fail completely. The operating system cannot reliably deliver the data based on the IP address alone. When every local connection shares the exact same address structure, local networking breaks down. The computer needs a physical tiebreaker to know which path to take. This typographic breakdown isolates the tail end of that original IPv6 address. The characters following the percent sign are what allow the operating system to finally differentiate between its various connections. The percent sign designates the zone ID, sometimes called a scope ID. It explicitly tells the computer which physical interface it should use to resolve that routing ambiguity. This split-screen comparison shows how operating systems format this ID differently. On the left, Windows uses internal numerical indexes, so the zone ID looks like %16 or %11 locking into a specific port. On the right side, Mac and Linux systems use direct interface names. Their zone IDs look like %ETH0 for an Ethernet port, or %EN0 for Wi-Fi. This terminal screen displays the exact command required to reach that printer. By typing ping fe80:2 %16, the user executes a highly targeted request. Mechanically, the operating system is receiving an explicit order. Send this data to the printer, but push it exclusively through the Ethernet port designated by the number 16. The zone ID provides a hard-coded physical exit route. It completely eliminates the need for the operating system to blindly guess which door to use. Once the operating system processes that command, the data packet leaves the hardware port and travels down the physical wire. But there is a critical mechanical constraint. When the packet crosses the exit port threshold, the %16 detaches. The zone ID is purely a local signpost. The system strips it away, so the cleaned FE80 packet travels seamlessly across the wire to the printer. This mechanic becomes increasingly necessary as our devices connect to overlapping, complex network environments. Virtual private networks and virtual machines, or localized smart home hubs, all create separate network zones on a single device. The zone ID prevents digital gridlock in these dense environments. It ensures our complex machines never shout blindly into the void, but always know exactly which door to walk through.